Hey everyone, Mr. Fransky here. I hope you're having a great day. Today we're going to just do a little intro to Chapter 10 and talk through 10.1. Chapter 10 is all about calculus and other systems, including parametric, vector, and polar systems. So we're just really taking everything we know and extending it to some different ways of graphing functions. Let's take a look. So what have we done calculus on so far? Where have we done it so far? So we've done calculus on things like y equals x squared, right? These are what are called Cartesian coordinates. They're named after Descartes. So Cartesian coordinates, you have an x value and it maps up to a y value or an f of x value, right? So you do something to an x and it gives you out a y. That is pretty much what we focused on all year. Another thing we've done is implicit. So implicit we did back in, I don't know, chapter 3, chapter 4, somewhere in there. That's like x cubed plus y cubed minus 9xy equals 0. Right, so we did the derivative on this. Remember, we had to do all the chaining. It was like 3x squared plus 3y squared y prime minus 9. Then we had to do product rule on this. So it would be y plus xy prime equals 0. And then we would have to factor out all the y primes and solve if we want to find the derivative, right? So that's really all we looked at so far. And what we're going to do now is we're going to focus on these three new things. So this is kind of just an intro to what we're going to be looking at. So a parametric equation, that's where you have x is a function of some parameter t, and y is as well. This is used a lot in computer science because, and then they'll give you like t is on some interval. Because in computer language, often you want to be able to do everything in terms of one single variable. And so being able to like get motion of a particle or something from one point to another. So it might be that when t equals 0, the particle is here, and then x and y behave based on time increasing. So maybe you're at this point by the time, I don't know, t equals 3 or something. So maybe t from 0 to 3. So being able to do things in terms of one variable instead of two, but still be able to graph them in 2 dimensions is important. This often relates to motion, but motion is usually given in terms of a vector. So vector is the calculus on vectors is pretty much the same as the calculus on parametrics. They write it with pointees instead, and this is almost always motion. Okay, so this is usually motion. So it'll give you like a velocity vector. Let's say the vector of velocity is, you know, cosine t, 2 sine of t, or something like that. And then you can find the acceleration and the position vector using those velocity coordinates. Polar is usually an r comma theta. So r is usually some function of theta. And this guy usually makes some kind of curves that are like curvy, kind of like swirly like this. So you may remember that from pre-calc where you have these like, I think some of the pre-calc teachers make you name them like limacon and rose curves and different flower petal things. Sometimes you get things that look like this, right? If I could draw correctly. Something like that, right? So anyway, just different systems, and the reason we still have to do calculus on these is because we might want to know, well, what's the slope right here? Or what's the area of this little loop right here, or the slope of the curve right there. But we're given it in different format, so we have to be able to somehow do calculus on these. So why? Why do we have to learn these? Because on the AP test, there is always, every year, a question about parametric and vector. Usually they're combined, but there's always a question. Usually it's a motion question in 2 dimensions. Every motion problem we've done so far has been boring. It's about a particle moving left and right on a line. It's moving left if the velocity is negative, right if it's positive. Now we're able to take particles and they can do whatever they want in 2 dimensions. So instead of being stuck to just the x-axis or the y-axis, they can move all over the place. Polar is a little bit more complicated and it's harder to predict. There was a polar question in 01, 03, 04, 05, 07, 09, and then they decided, well, this is too predictable, so they went to 13, and 14 also had a polar problem, and they skipped till last year, so 17. So they had 2 years in a row. They might have 2 years in a row again, or maybe they won't. I don't know, but we've got to learn it just in case there's going to be a polar question on the test. So today what we're going to focus on is parametrics, but before we do that, I just want to mention that the calculus isn't harder, it's just different, and there are lots of equations that we have to learn to be able to do these things in other systems. And that's why we kind of save it for the end, because there are all these equations. It's like, well, hopefully we can cram them in and you'll remember them for the AP test. That's kind of the goal. So today we're going to focus on 10.1, which is parametric functions, and we're going to learn about slope, concavity, and arc length in this video. So first the question is, what the heck is a polar or a parametric function? So a parametric function is when where x and y are determined in this parameter t. It's called the parameter. Hopefully you learned about this in pre-calc. Okay, so t is a parameter that defines both x and y. So often what you'll do here is you'll make a t, x, y chart, After you do a few of these, you don't really have to do this anymore. But when t is 0, we're going to have cosine of 0 for x and sine of 0 for y. Cosine of 0 is 1, sine of 0 is 0. So now, because we're going from 0 to 2 pi with t, we're going to think, well, what are easy to take cosine and sine of? Well, maybe like, I don't know, pi over 4. So I do pi over 4, both cosine and sine will be root 2 over 2. Then maybe I do pi over 2. At pi over 2, cosine is 0, sine is 1. Then maybe I'll skip to pi. At pi, cosine is negative 1, sine is 0. Then maybe we go to 3 pi over 2, the bottom of the circle. So at 3 pi over 2, cosine is 0, sine is negative 1, and then all the way at 2 pi, which isn't really included, but it's going to get really close to it, cosine is 1 and sine is 0. So if we were to graph this, thing, we start off at 1, 0. That's when t equals 0. Then when t is pi over 4, we're at root 2 over 2, root 2 over 2. That's it right there. So t equals pi over 4. Then we're at the top when we get t equals pi over 2. And then we're over here at pi. We're down here. It looks like we're making a circle. In fact, we're making the unit circle. If I had put those points where they were supposed to be. So time is increasing. Sometimes you'll see arrows on a graph like this because this is as time increases, right? So we've created a circle. We've created the unit circle just by using a single parameter, right? And then we use x and y are functions of that single parameter t. Now the nice thing here is that in rectangular coordinates or Cartesian coordinates, the equation for the unit circle is y equals plus or minus the square root of 1 minus x squared, which is gross. Often you can do things with parametric equations that make the rectangular equations a lot more elegant and kind of simple to deal with. That's kind of why we do this. So now again, as I said before, I might ask, well, what's the slope when t equals like 5 pi over 6? So we'll get there. We'll get there. We're going to learn that formula today. So we'll get there soon. Oop. But being able to find the slope of something like this is kind of the new thing that we're going to be doing today, and also talking about concavity and length of a curve. So if you wanted to check, if you solve this for this, the equation of the circle is 1 equals x squared plus y squared. So we can check to see if the parametric works. If we substitute cosine in for x and sine in for y, we have 1 equals cosine squared t plus sine squared t. Does that work out? Yes, it does, because sine squared plus cosine squared is always 1. Nice. All right, let's try one more. So this one's similar to the last one. We have 3 cosine t and 2 sine t. So the way I think about this is cosine is maximized at 1. So this goes from negative 1 to 1, and this goes from negative 1 to 1 as well. Let's think about it now. So now 3 cosine t, that can go from negative 3 to 3. 2 sine t can go from negative 2 to 2. Any guesses what this might create? They should be brackets, I guess. Well, if cosine can now go out to 3 and sine can go to 2, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. I think it's going to make an ellipse. How much easier is that than the way you learned ellipses in pre-calc, right? So the equation for this ellipse in pre-calc terms would be, let's see, x squared over 9 plus y squared over 4 equals 1. Remember, you do x squared over a squared, y squared over b squared for the length of the semi-major and semi-minor axes. And if you plug 3 cosine t in here, you'll get 3 squared, which is 9. The 9s will cancel. You'll have cosine squared plus the 4s will cancel over here. Sine squared plus cosine squared, 1 again, right? So it works out that when you substitute those in to change the parameter to Cartesian, that does work out. So that's pretty nifty, that we can just make an ellipse by using parametrics so much easier by just changing these, right? This is really just like a scale change to the parametrics from before. And you can kind of do them, think about them independently, right? This just changes the x, this just changes the y. It's really easy to do changes on these things. Let's try one now that's kind of more like we've seen before. So if you have x is root t, y is t minus 2, let's make a txy chart here. And we're going from 0 to 4. So let's just go 0, 1, 2, 3, 4. So x at 0 is 0. X at 1, square root of 1 is 1. Here we have root 2. Can't really do anything about that. Root 3 either, but then we have positive 2. The y values, we're just subtracting 2. So we have negative 2, and then negative 1, then 0, then 1, then 2. So let's see, we have 0, negative 2, so I'm just plotting these x comma y. Then we have 1, negative 1, right there. And then we have root 2, 0. Root 2 is like 1.4, so that's going to be like right there. Then we have root 3, 1. It's going to be like right there. Root 3, I think, is like 1.7 something, I think. And then 2, 2. Right there. Oh, that was pretty terrible. 2, not 3, Fransky. There we go. Okay, so it looks like we're creating a parabola here. Okay, and if it stops here, then I should stop it there. I really shouldn't have that extra bit on there. And we go from 0 to 4. It's kind of a directed curve going in this direction. So this looks a lot like a parabola, and we can actually prove that. So I'm going to tell you to eliminate the parameter. And in that case, what you want to do is you want to just solve it in terms of x and y. So I have right now x equals the square root of t. Whoops. And I have y is equal to t minus 2. What I'm going to do is I'm going to solve either one of these for t. Usually I like to solve x for t because then I can just leave it as y equals. So this means that t is equal to x squared. Now I can just plug that into the t on the bottom one. So y is x squared minus 2. Okay, so we've gone from parametric to rectangular or Cartesian. And we can see that, right? This is exactly what it looks like. It looks like the parabola, and it's just been moved down 2 units. Okay, nice. So we're going to do calculus kind of on this one first because it's something we know something about. And let's just see if we can figure out some formulas first. So how about slope? What are we going to do for slope of a parametric? So what we know is we've been doing things like y equals natural log x, right? This function looks like this. And if we want to know the slope at any point x, we can find it, right? The whole idea of derivative is the slope at any point x. So y prime derivative of natural log is 1 over x. So we know that at any x, so like when x equals 5, the slope of that is going to be 1/5, right? The slope of that tangent line to the curve is going to be 1/5. So with parametric, what can we do? So how about parametric? So the problem here is that we have x is some function of t, and y is some function of t. But what I still want dy dx. So what we're going to do is we're going to use some fancy algebra to be able to kind of tease dy dx out of this equation. So like let's think about when we had like x equals cosine t and y equals sine t. So we might not know how to get dy dx right away, but can we do something with the functions of t? Well, I'm pretty sure I can get dx dt, and I'm pretty sure I can get dy dt, right? So dx dt in this case would be what? Negative sine of t, and dy dt would just be cosine of t. Now, do you see anything we could do with algebra on these two to end up with dy dx? I want to get rid of the dt's. Remember when you divide, you can like multiply by a reciprocal? I think if we do dy dt and we divide by dx dt, let's see if it works. That's going to be dy dt times dt dx. The dt's cancel and we end up with dy dx. Check that out. So this is the formula you need to know. Dy dx is just the division of dy dt over dx dt. So if you have x as a function of t and y as a function of t, take the derivative of both, put the y one on the top, and you have your dy dx. So the derivative of a function, if you want to know the slope of a curve in terms of y and x, you just do the derivative of y divided by the derivative of x. Now, if you need more proof, think about y as a function of x of t, and we take the derivative then. Use chain rule. So f prime of x, leave the x of t alone, and then you multiply by x prime of t. So if you want to know f prime overall, so you want f prime of x basically, just divide by x prime of t. So we have y prime of t divided by x prime of t equals f prime of x. That's it. Okay, because sometimes the dividing of like differentials with this is kind of weird to cancel them out, but same thing either way. Okay, so dy dx is the derivative of y divided by the derivative of x. That's important. Make sure that's in your notes. Okay, so new stuff, same old rules. So remember back we did like in chapter 3, chapter 4, somewhere in there, we talked about like horizontal tangents, vertical tangents. So a horizontal tangent. Remember, what does that mean about the derivative? If we have a horizontal tangent, that means our derivative would be 0, right? So that means dy dx equals 0. Well, the only way to make a fraction like this 0 is if the top is 0. So that means that dy dt must equal 0. They like to ask questions about that a lot. They say, like, when does this thing have a horizontal tangent? You don't have to worry about x at all. All you have to worry about is making sure that the y derivative is 0. Now, because we are in the realm of being able to do things like this now, we might ask about a vertical tangent. Well, a vertical tangent is going to happen when dy dx is undefined. And that would be when dx dt is 0. Now, of course, if they're both 0, you have an indeterminate form, and you have to figure out what's going on with that, right? It might not be a vertical or a horizontal tangent. It could be something weird happening, whereas you have to figure out that limit, maybe using L'Hopital. But In general, that's what's going to be going on. And then a tangent line, nothing changes about the tangent line. Tangent line, what does it always need? Point and a slope. So the point you would find, if they say like at t equals 1 or something, then you would just do x of t0, comma y of t0. So whatever that t is that they give you, t0, that's going to give you the point. The slope, just remember, dy dt, over dx dt. So dy dt over ex dt is going to be able to find that slope for you. And it's just always just y minus y1 equals m times x minus x1. And that's where x1 and y1 are whatever you get from those t's. So let's try that with that. Let's try it. So here's one we know. So we know this parabola, we already found it. It's just y equals x squared minus 2. So we're going to find the equation of the tangent line to the curve when t equals 1. So when t equals 1, we need a point and a slope. Point. T equals 1, so we're going to have root 1, comma 1 minus 2, which is 1, comma negative 1. That makes sense. That's right there. Okay, so our slope there, I think our slope there is going to be 1, but let's see if we can figure it out. Because if you do this, let's see, we would have, maybe it's 2, because y prime would be 2x. So 2 times 1, so value of x equals 1, should be 2. Let's see if that happens with using our formula. So the slope is going to be dy dt over dx dt. Dy dt is just 1, right, because it's just the derivative of t minus 2. Dx dt, so we have t to the 1/2. So the derivative is going to be 1/2 t to the negative 1/2. That is 1 over 2 root t. You might remember that from back when we did a lot of these. So 1 over 2 root t. Multiply by the reciprocal, that's just 2 root t. And we evaluate that at t equals 1. That gives us 2. Okay, and that was what we got using Cartesian as well. I'm going to do one with Cartesian so we can prove that it works. So now we should put it in a point slope form. So we got y plus 1 equals 2 times x minus 1. Bingo. Lovely. Alright, moving right along. How about concavity? So for concavity, remember we need the second derivative. That's d squared y dx squared. Now, one thing that's tempting to do, but don't do it. One thing that's tempting to do is to do the second derivative of y dt and divide by the second derivative of x dt. That is not right. Okay, so you can't just do the second derivative at the top and the second derivative at the bottom, and I'll show you why. Because y double prime, so let's think about it this way. So the derivative, dy dx, another way to think about that is just d dx of y, right? We've seen this before. You take the derivative and you just plug the function in front of it, and that means take the derivative of the function. So that is d dt of y divided by dx dt. And the dt's come up and cancel, you have dy dx. So the derivative of y prime, d dx of y prime, would then be the derivative with respect to t of y prime divided by dx dt. So notice the dx dt does not get a second, like a second derivative on it. So the way to think about this is it's going to be d dt of dy dx. So you take the derivative of the derivative with respect to t, and then you divide by dx dt again. This is the formula for y double prime. Okay, so basically what you have to do, so steps for doing this. First thing you do is find the first derivative. So find y prime, which we know is dy dt over dx dt. This will have t's, so it has t's in it. Okay, for our last problem, our dy dt was 2 root t, right? So now the next thing you're going to do is derive y prime, so our 2 root t from before, or whatever it is, with respect to time. Okay, so you're going to derive with respect to time. That'll be on the top, right? So you basically, this is our 2 root t in our last example. So you derive that with respect to time. So that would be what? 1/2 times 2 is just 1, so it would be 1 over root t. Okay. And then last thing is you divide, again, by dx dt. Okay, so you divide by whatever dx dt was to begin with, and that will give you your second derivative. Okay, let's try that. So show that root t comma t minus 2 is concave up on t from 0 to 4. So we already know that y prime is 2 root t. We got that by doing dx dt, or sorry, dy dt divided by dx dt. Okay, so then the y double prime is going to be the derivative of 2 root t divided by dx dt again. Let's see, remember dx dt. Dx dt was 1 over 2 root t. So this is 1 over 2 root t. Okay, so the derivative of 2 root t, the 1/2 comes to the front and cancels. We get a negative 1/2. So we got 1 over root t divided by 1 over 2 root t. Multiply by the reciprocal, we got 2 root t divided by root t. Root t's cancel. That is just 2. Well, 2 is always positive. So this means that xy equals root t comma t minus 2 is always concave up. Not only from 0 to 4, but everywhere, which makes sense because we know it's a parabola like this, which is always up like a cup. Cool. All right, moving right along. So I have an example here where calculus is okay. Or calculator, not calculus. I've got a calculator ready to go, so let's see how we do here. So we have t squared minus 5 and 2 sine of t from 0 to pi. I don't really know what this would look like. So first thing let's do is find the maximum xy from 0 to pi. So remember when you have a closed interval, I guess it's maybe be closed. You want to check endpoints and also critical points. So we first have to find the derivative. So y prime dx dt, no, I keep mixing that up. dy dt over dx dt. So dy dt, let's see, that would be 2 cosine t, divided by dx dt, which is 2t. So I want to know when this is equal to 0. That's going to be my critical point. So that's going to happen whenever 2 cosine t equals 0. I'm not even going to have to use a calculator for this one. So cosine is 0 at pi over 2. That's the only one on 0 pi that's going to work. So I have to think about pi over 2 here. So prior to pi over 2, let's think about the derivative here. Prior to pi over 2, we're going to have a positive on the bottom. This whole time we have positive on the bottom, right? From 0 to pi. Cosine, though, before pi over 2, we have positive values of cosine. After pi over 2, if we think about the unit circle, we have negative x values over there. So we have negative values. So we start on a low value. We rise up to a value at pi over 2, and then we drop back down to some lower value at pi. So that means our maximum must happen at pi over 2. So the max is at x equals pi over 2. And they want us to find x comma y. So we're going to have pi over 2, comma, now we have to find the y value. 2 sine of pi over 2. Sine of pi over 2 is 1, so it's going to be up at 2. Okay? Now they want us to find the inflection point. Any inflection points that there are. So for that we need y double prime. We'll do that here, and then on the next page we'll kind of figure out what when it's 0. So y double prime in this case, remember it's going to be d dt of our first derivative, y prime, and we divide by dx dt. So that's going to be the derivative of our y prime, which is 2 cosine t over 2t, yuck. Looks like we're going to have to use quotient rule there. Then we divide by dx dt again, which is still 2t. So, derivative of the top, low d high, 2t times negative 2 sine t, minus high d low, that's 2 cosine t times 2. Over the square of low we go, which is 4t squared. And that's all divided by 2t. Alright, let's simplify that on the next page maybe. Well, let's see if we can squeeze it in here. So we have, let's see, negative 4t sine t minus 4 cosine t over 4t squared times 1 over 2t. So I just basically slid this entire thing off. Right? So I have 1 over 2t multiplied by that whole thing. Let's see, these 4's all cancel. Right? You factor the 4 out of the top technically and then divide with the 4 on the bottom. So it looks like our derivative is negative t sine t, excuse me, minus cosine t divided by 2t cubed. Okay, so that is our second derivative. So we should probably find out when that thing is 0. From 0 to pi. So we have our number line here, 0 to pi. I have to figure out when that thing is 0 and see if it changes sign. So I'm just going to graph that on my calculator. Okay. There we are. Let me go to my graph. And I'm going to graph negative, let's put this in parentheses, negative t sine t, t times sine t I probably need to make sure that it changes from that italics. And then minus cosine t, close parentheses, divided by, parentheses, 2t cubed. Alright, let's see what we get. Oh, should probably use x's instead. Use an x on the top. There we go. Perfect. Where's my t? Oh, I still have one. There we go. Now it'll be happier. Okay, so I'm going to change my window from 0 to pi, which is like 3.1415, and that'll be fine. Okay, so it looks like it only maybe crosses one time over here. So I'm going to go to Menu, Analyze Graph, 0. Lower bound is fine at, here is fine. And over here, up, there we go. We got 1 0 at 2.79839. Let's write that down. 2.79839. Go back to blue. Right here at 2.79839. And that was the only time that it changed sign. We went from negative to positive. Like, so we go from concave down to concave up. So that's the only time that's going to change. So that's our t value. So they asked for the actual xy coordinates, I'm pretty sure, which is annoying. So we're going to have to do 2.7839 squared minus 5, comma, 2 sine of 2.79839. And there's our point where the inflection point happens. Fun, fun, fun. Alright, moving on. I think our last thing we're going to do is arc length, and then we get out of here. Arc length formula is actually really easy. So remember what we learned about arc length. Let me turn my page here. So we learned about arc length back when we did this with sorry, I'm just looking at my notes here. Back when we arc length with Cartesian. Alright, so with Cartesian coordinates, we had something like this. I remember drawing this picture on the board, and we said we had a start point and an end point. And we had delta x, and we had delta y, and then we really wanted to find that hypotenuse. And we knew the hypotenuse was the square root of delta x squared plus delta y squared. And the problem was we didn't really want it to look like this. We wanted it to look like something about like a delta x at the end. So something in there, a delta x at the end. And what we ended up doing was we had to integrate from a to b, x value, square root of 1 plus the derivative squared. That's what we had to do. dx. So basically what we did was we kind of had we pulled out a dx from both of them, from the delta x squared and the delta y squared, and then we created this derivative by a delta y over delta x. In parametric, it's way easier. This is dx dt, sorry, dx squared, and then dy squared. What we do is we divide by dt squared for both of them, and then multiply by the square root of dt squared, and that's just dt. So we end up with just the integral from t1 to t2, the square root of dx dt quantity squared, plus dy dt quantity squared. So really it's just Pythagorean theorem, and that's all dt. So make sure you have that formula in your notes. That was a really quick proof, not even really a detailed proof, but it works pretty much the same way as the old one. It's just that now we have both dx dt and dy dt. We don't have to worry about knowing dx and dy to be able to find that hypotenuse. Okay, so we're just going to do one of these with no calculator, and that's it. So we got cosine cubed and sine cubed from 0 to 2 pi. So what I'm going to do here is I want to show you this in Desmos, because it's pretty cool how you can use parametrics in Desmos, actually. So what I'm going to do is I'm just going to graph cosine cubed t, sine cubed t. So what you do is just put in parentheses cosine, I'm going to do it like this, t cubed, comma, sine of t, close parentheses, cubed. And notice they know right away that you want to do it with parametrics. So they have t going from 0 to 1. I think we want t to go from 0 to 2 pi. So I'm going to make this go to 2 pi. There we go. Hey, look, it makes kind of like a diamond thing. So we want to find the arc length here. What we might be interested in doing is kind of seeing, well, what's going on here on this curve. Let's see if they'll let me trace it. I don't know if they will. No. But what I can do, there's a way to make kind of a tracer for a parametric like this. What you can do is you can do cosine, you just use an n instead. Comma, sine n cubed. Add a slider, and this should create a point. So now what we can do is we kind of slide along and we can see what's going on. So I want this slider to go from 0 to 2 pi. And we'll step it. That doesn't really matter. Right. So now, what we can see is at 0, it starts over on the right there. As we increase, we go up to the top, then we come down, then we go to the bottom, then we go to the right. So in 2 pi, we make 1 full cycle. So that must mean that from 0 to pi over 2, we do that first part. It should be about pi over 2 there. Yep, about 1.5. So what I'm going to do is I'm just going to find the area, the length of that first part, and then I'm going to multiply it by 4. That's really useful, the symmetry thing, because sometimes what happens if you integrate from 0 to 2 pi, it'll turn into 0. So what I'm going to do here, so we're going to use our formula. So we're going to integrate from t1 to t2, square root of dx dt squared, plus dy dt squared, dt. So we're integrating from 0 to pi over 2, we say, because we're just going to do a quarter of it. Square root of the derivative of x. So that's going to be 3 sine, excuse me. Nope, no, sorry, leave the inside part alone. So we have 3 cosine squared t times derivative of the inside, which is negative sine t, plus the derivative of y, which is 3 sine squared t times cosine t, all that dt. Now the inside here looks messy, but I think we can factor some stuff out that's going to make it a lot easier. So let's see here. We have 0 to pi over 2. Square root. Looks like we have 3. So we have cosine squared. Looks like we can take out a 3 for sure. And then we can take out a sine cosine from both of them. Is that right? Let's see here. I think that's what I want to do. Oh, I forgot to square the derivatives. This whole thing should be squared. And this whole thing should be squared. I knew I forgot something. Because I have to square the derivatives, right? So we have the square root of, let's see, it's going to be 9 cosine to the 4th t sine squared t, and the negative will disappear. And then we'll have plus 9 sine to the 4th t cosine squared t. There we go. dt. So now it looks like I can factor out a 9 cosine squared sine squared. So we have integral 0 to pi over 2, square root of 9 cosine squared t sine squared t, times, so what am I left with? Cosine squared t plus sine squared t. And that part is just 1, because cosine squared plus sine squared is always 1. Square root is going to cancel that out. So we have integral 0 to pi over 2. We have 3 cosine t sine t dt. And now let's see about deriving this. I think we can use u sub on this, right? If we do u is, let's do sine t. Then du is cosine t dt. We have that, cosine t dt right there. So we have 3 integral. Let's change over to u land. So sine of 0 is still 0. Sine of pi over 2 is 1. So now we just have u du. That is 3 times u squared over 2 from 0 to 1. The 0 gives us nothing, so we have 3 times 1/2, which is 3/2. So arc length for this thing, 3/2, not too bad at all. But I messed up, right? Because 0 to pi over 2, so we have 4 of those. 4 times 3/2 is 12/2, which is 6. So it's 3/2 just for that first little bit, and then their whole thing turns out to be 6. I think I have another blank thing here because I thought that I was going to need more space, but I didn't. And so that's all I've got for you. Love you guys. That's why I'm here. Have a great day. Thanks for listening. Look forward to doing more with vectors and polar coordinates when I see you again. Talk to you guys later. Bye-bye.